Right now, as you're watching this video, over 60% of stars exist in binary systems, but you only see one shadow. The first confirmed planet orbiting two stars, Kepler 16b, proved that worlds with double shadows actually exist. But that's just the beginning of what we've discovered about planets that break Earth's rules. The James Webb Space Telescope and TESS have confirmed worlds like HD 189733b, with sideways metal rain moving faster than bullets, Kepler 138 with ocean layers thousands of kilometers deep, and Corot 7b, where vaporized rock condenses into solid precipitation. These discoveries reveal three categories of impossible phenomena: binary shadows that shift throughout alien days, ocean worlds deeper than we ever imagined, and exotic weather that turns physics upside down. What you consider normal about Earth is actually the cosmic exception. Multiple shadows on binary star worlds. The first place to understand this cosmic exception is in the binary star systems that dominate our galaxy. Over 60% of all star systems contain two or more stars locked in gravitational dances around each other. These binary and multiple star systems are the norm, not the exception. Our solitary sun makes us the odd ones out in a galaxy filled with stellar partnerships. The Kepler Space Telescope and TESS have now confirmed over 80 circumbinary planets, with statistical analysis showing that roughly 1 in every 12 binary star systems hosts at least one planet. These aren't theoretical worlds anymore. They're real places where the fundamental experience of existing would be completely different from anything you know. Each new discovery reveals more about how these complex systems actually work. Standing on Kepler 16b, the first confirmed circumbinary planet discovered by Kepler, would immediately show you how strange these worlds really are. This planet, roughly the size of Saturn, orbits two stars that are locked in their own cosmic waltz. One star burns orange-red while its companion shines brilliant white. As the planet moves through its 229-day orbit, the relationship between these two light sources creates shadow patterns that change constantly throughout each day. Your shadow wouldn't just move across the ground like it does on Earth. It would split, merge, disappear entirely, and reappear as multiple distinct shadows depending on the positions of both stars. The orbital mechanics that make this possible challenge everything scientists thought they knew about how planets form. For decades, researchers believed that the gravitational chaos of binary systems would prevent planets from maintaining stable orbits. The competing gravitational pulls should tear apart any forming worlds or fling them into deep space. Yet these planets exist and maintain stable orbits for millions of years. Computer simulations now show that planets can find gravitational sweet spots where the pull from both stars actually stabilizes their orbits rather than destroying them. Each day on these worlds brings multiple sunrises and sunsets as the planet's rotation reveals and hides each star in sequence. On some binary planets, you might watch the orange star set in the west, while the white star continues to burn overhead, casting your shadow in a completely different direction. Hours later, as the white star approaches the horizon, the orange star might rise again from the east, creating a second dawn before the first day has truly ended. The concept of a single 24-hour day becomes meaningless when you're dealing with two different light sources that operate on their own schedules. TOI 1338b, confirmed as the first circumbinary planet discovered by TESS, demonstrates another variation of this shadow complexity. This world, roughly 7 times the size of Earth, experiences even more dramatic shadow shifts as it orbits its binary pair. The changing angles between the planet and its two stars create periods when shadows appear sharp and distinct, followed by times when multiple overlapping shadows create complex patterns across the surface. Navigation on these worlds would require completely different methods than anything developed on Earth. Among the 20 to 30 well-studied binary systems, traditional sundials become useless when multiple shadows point in different directions at the same time. The concept of using the sun's position to determine direction breaks down when you have multiple suns that move independently across the sky. Any civilization that developed on such worlds would need to create time-keeping systems based on the complex interactions between multiple light sources rather than the simple rotation of a single star. The daily rhythms of life would be completely alien to anyone from Earth. Instead of the familiar cycle of day and night, these worlds experience periods when multiple stars shine simultaneously, creating intensely bright conditions where shadows appear sharp and distinct. Other periods bring partial darkness when only one star remains visible, creating dim twilight conditions even during what would normally be considered daytime. Some binary planets experience true darkness only when both stars set simultaneously, which might happen just once during each orbital period or not at all depending on the planet's axial tilt and orbital characteristics. Temperature variations on these worlds follow patterns that make no sense from an Earth perspective. A planet might experience its warmest period when both stars shine directly overhead, creating intense heating that far exceeds anything possible with a single star. Conversely, when the planet's orbit carries it farther from both stars simultaneously, temperatures might plummet rapidly. These temperature swings happen on timescales completely different from Earth's predictable seasonal changes. The implications extend beyond just shadows and temperature. Photosynthesis on these worlds would need to adapt to light sources with different spectral characteristics. Plants or plant-like organisms would need to handle the orange-red light from one star and the bright white light from another, possibly at the same time. The evolutionary pressures on such worlds would create life forms adapted to multiple light sources rather than the single spectrum we're familiar with. What makes this even more mind-bending is the realization that our single star system is actually the cosmic oddity. Earth's simple pattern of one shadow following you around during the day is unusual in a galaxy where most worlds experience the complex interplay of multiple light sources. The familiar rhythm of single sunrises and sunsets represents a minority experience in the universe. These binary worlds aren't rare exceptions or exotic curiosities. They're the standard configuration for planetary systems throughout our galaxy. The strange worlds are places like Earth, where planets orbit alone around solitary stars, creating the simple shadow patterns we consider normal, but which are actually quite rare in the broader cosmic context. But shadows are just the beginning of how alien worlds break the rules we think are universal. Ocean worlds deeper than imagination. The deepest point in Earth's oceans reaches down 11 kilometers below the surface. That's the Challenger Deep in the Mariana Trench, and it represents the absolute limit of how far down water goes on our planet. Scientists used to think that even this depth was extraordinary, and that any ocean worlds discovered around other stars might have similar or perhaps slightly deeper water layers. The 2025 atmospheric analysis data has completely shattered that assumption and revealed ocean worlds that make Earth's deepest trenches look like shallow puddles. Spectroscopic observations from the James Webb Space Telescope have revolutionized our understanding of what constitutes a deep ocean. The updated atmospheric composition data from newly analyzed exoplanets shows water layers that extend not just tens of kilometers down, but hundreds or even thousands of kilometers beneath the surface. These aren't just planets with oceans on top of solid surfaces like Earth. These are worlds where water dominates the entire planetary structure from the surface down to depths that challenge our ability to comprehend them. K2-18b serves as the perfect example of how wrong our previous assumptions were about ocean depth limits. This sub-Neptune exoplanet, located 124 light-years away, initially seemed like just another potentially habitable world when it was first discovered. The 2025 spectroscopic analysis has revealed an atmospheric composition that indicates water vapor, methane, and carbon dioxide in concentrations that suggest something far more extreme than anyone expected. The data shows that this planet likely has a water layer that could extend over 1,000 kilometers deep, making it fundamentally different from any ocean world we previously imagined. Recent spectroscopic analysis of similar exoplanets has confirmed that these extreme ocean depths are not unique to K2-18b. Kepler 138c and Kepler 138d both show density measurements that indicate water comprises a massive percentage of their total planetary mass. unlike Earth, where water accounts for just 0.02% of the planet's mass despite covering most of the surface. These ocean worlds contain water that represents anywhere from 10% to 50% of their entire planetary mass. This means that instead of a thin layer of water sitting on top of rock, these planets are essentially giant water spheres with rocky cores buried thousands of kilometers below the surface. The physics of water under such extreme pressure and depth creates conditions that don't exist anywhere on Earth. As you descend through these impossibly deep oceans, the pressure increases to levels that fundamentally change how water behaves. At depths of just a few hundred kilometers, the pressure reaches millions of times Earth's atmospheric pressure. Water molecules get compressed so tightly that they can no longer move freely, yet they don't freeze in any way that would be recognizable to someone from Earth. These crushing depths create exotic forms of ice that exist in states impossible to replicate naturally on our planet. Ice 7 forms when water molecules are forced into crystalline structures under extreme pressure, while remaining at temperatures that would normally keep water liquid. This ice stays solid even at temperatures exceeding 100 degrees Celsius because the pressure is so intense that the molecules cannot break free from their rigid arrangement. Laboratory experiments have confirmed that Ice 7 can exist at pressures starting around 30,000 times Earth's atmospheric pressure, which would occur at depths of just 300 kilometers in these deep ocean worlds. Even more exotic is superionic ice, a phase of water that was only recently confirmed to exist through laboratory recreation of the extreme conditions found in these deep alien oceans. In superionic ice, the oxygen atoms lock into a rigid crystalline lattice, while the hydrogen atoms flow freely through this structure like a liquid. This creates a form of ice that conducts electricity like a metal while maintaining the structural properties of a solid. The discovery of superionic ice in 2025 laboratory experiments confirmed that this bizarre state of matter must exist in the deepest layers of extreme ocean worlds, creating environments where the boundary between solid and liquid becomes meaningless. The question of what kinds of life could theoretically survive in such environments pushes the limits of astrobiology. The extreme pressure alone would instantly destroy any life form that evolved in Earth-like conditions. At depths where superionic ice forms, the pressure exceeds anything that even the most extreme deep-sea creatures on Earth can withstand. Yet the presence of liquid water, even under these extreme conditions, means that some form of life adapted to these pressures might theoretically exist. The 2025 updates on subsurface ocean discoveries in our own solar system provide an interesting comparison to these extreme exoplanet oceans. Europa's subsurface ocean extends roughly 100 kilometers deep, while Enceladus has a water layer about 30 kilometers thick. These depths seemed impressive when they were first confirmed, but they pale in comparison to the 1,000-kilometer deep oceans found on distant exoplanets. Even Titan's subsurface water ocean, which extends roughly 200 kilometers down beneath its icy crust, represents just a fraction of the water depth found on these extreme ocean worlds. The alien physics at work in these deep ocean worlds creates environments where normal chemical processes operate under conditions that exist nowhere else in the solar system. Chemical reactions that would be impossible under Earth conditions become commonplace when water molecules are compressed into exotic ice phases. Temperature gradients in these deep oceans follow patterns that make no sense from an Earth perspective. While Earth's oceans get colder as you descend, these extreme ocean worlds might actually get hotter toward their centers due to the immense pressure and possible radioactive heating from their rocky cores. The scale of water on these ocean planets defies comprehension when compared to Earth's relatively modest water reserves. Some of these worlds contain more water than thousands of Earths combined. A single ocean planet might hold more liquid water than exists in every ocean, lake, river, and ice cap in our entire solar system multiplied by several thousand times. But water isn't the only substance that behaves in impossible ways on alien worlds. The atmospheric conditions on some planets create precipitation that makes Earth's most extreme weather look ordinary. Diamond rain and crystal weather. Neptune, and Uranus demonstrate just how extreme these weather systems can become when atmospheric conditions reach levels that Earth cannot naturally produce. These ice giants operate under pressures that exceed anything on our planet by factors of millions, creating weather patterns where diamonds literally fall from their skies like snowflakes. This isn't theoretical anymore. Laboratory experiments conducted throughout 2024 and 2025 have successfully recreated the exact pressure and temperature conditions found in these planetary atmospheres, confirming that diamond precipitation actively happens on worlds in our own solar system right now. The process requires crushing pressures that compress carbon atoms into diamond crystal structures, while temperatures soar beyond 2,000 degrees Celsius. Deep within Neptune's atmosphere, methane molecules break apart under these extreme conditions, releasing carbon atoms that get compressed so intensely they form solid diamond crystals. These diamonds then fall through the atmospheric layers like hail, except each piece represents crystallized carbon worth thousands of dollars by Earth standards. Laboratory recreation of these conditions involves using powerful lasers to generate the precise pressure and temperature combinations found in ice giant atmospheres. Scientists at Lawrence Livermore National Laboratory have successfully created diamonds using these techniques, proving that the atmospheric conditions on Neptune and Uranus naturally produce the same results. The experiments show that diamond formation occurs rapidly under these extreme conditions, with carbon atoms organizing into crystal structures within nanoseconds of reaching the required pressure thresholds. The scale of diamond production on these worlds defies comprehension. Neptune's atmosphere contains enough methane to fuel diamond precipitation for billions of years. Every year, the planet produces more diamonds than have ever been mined in Earth's entire history. These diamonds don't accumulate on a solid surface like they would on Earth. Instead, they continue falling through the atmospheric layers until they reach depths where the pressure becomes so intense that even diamonds get crushed into different forms of compressed carbon. Other exoplanets push exotic precipitation patterns even further beyond Earth's possibilities. WASP 121b experiences temperatures exceeding 3,200 degrees Celsius on its day side, hot enough to vaporize most metals and gemstones. The night side temperatures drop to around 1,500 degrees Celsius, creating conditions where vaporized metals can condense into clouds and then precipitate as liquid metal rain. Iron, magnesium, and other metals fall from the sky in liquid form, creating weather patterns where molten metal storms sweep across the planet's surface. The atmospheric composition data from 2025 observations shows that WASP 121b's atmosphere contains clouds made of iron and various minerals, including perovskite, forsterite, enstatite, and corundum. Corundum precipitation means that rubies and sapphires literally fall from this planet's sky. The extreme temperature gradient between the day and night sides creates a constant cycle where metals vaporize on the hot side, get carried by atmospheric winds to the cooler side, condense into clouds, and then fall as gemstone and metal precipitation. WASP 17b presents another example of impossible Earth weather through its crystalline quartz precipitation. This tidally locked gas giant maintains dayside temperatures hot enough to melt steel, while its twilight and dawn regions experience conditions that allow silicon dioxide to condense into fine crystalline quartz clouds. These aren't water clouds with quartz particles mixed in. The entire cloud structure consists of crystallized quartz that eventually precipitates as glass rain falling through the planet's atmosphere. Standing on the surface of any of these worlds during a precipitation event would be immediately lethal for multiple reasons beyond just the exotic materials falling from the sky. On Neptune, diamond hail would strike with velocities determined by the planet's gravitational acceleration and atmospheric density. Each diamond fragment would impact with enough force to penetrate any material known to exist on Earth. The atmospheric pressure alone would crush any Earth-based life form instantly, but the addition of high-velocity diamond projectiles falling continuously from above would make survival impossible even with theoretical protective equipment. The temperatures required to maintain liquid metal precipitation create environments where conventional weather patterns break down completely. on WASP 121b. The concept of a refreshing rain shower becomes meaningless when the precipitation consists of molten iron at temperatures exceeding 1,500 degrees Celsius.